Hello, everyone, and thank you for joining us. My name is Amanda Kramer, and I am the Alumni Engagement Program Manager at the University of Colorado Boulder's Lead School of Business. These are certainly trying times, and here at CU Boulder, we have gathered our world-renowned faculty and alumni to provide frank and timely insights for life during and after the COVID-19 pandemic. Today is the fourth of 7 webinars in this final spring COVID-19 related webinar series. To view upcoming webinars, please visit our website at colorado.edu/business/alumni. Click the drop-down arrow and click Attend Online Webinars. For today's webinar, we're so excited to have CU Boulder Assistant Professor in the Department of Civil, Environmental, and Architectural Engineering, Dr. Kyri Baker, here presenting How is COVID-19 Affecting the Electric Power Grid? A few housekeeping items before we begin. First, if you have any questions now or during the presentation that you would like to ask Kyri, please send a question through the Q&A interface. We will monitor questions as they are submitted, and Kyri will respond to them at the end of the presentation. As a reminder for optimum audio quality, we do have everyone on mute except for myself and our speaker. If you experience any technical difficulties during the webinar, please notify us through the chat interface and one of our support specialists will touch base. Lastly, a link to access the webinar recording will be sent to all registrants tomorrow, along with a survey link and supplemental resources from today's presentation. Now, I'm excited to introduce today's speaker. Dr. Kyri Baker is an assistant professor in the Department of Civil, Environmental, and Architectural Engineering, as well as the Electrical, Computer, and Energy Engineering by courtesy at the University of Colorado Boulder. Previously, Kyri was at the National Renewable Energy Laboratory in both the power systems and building centers. She received her BS, MS, and PhD in electrical and computer engineering from Carnegie Mellon University in 2009, 2010, and 2014, respectively. Her interdisciplinary research focuses on developing techniques to improve renewable energy integration within the electric power grid, with an emphasis on optimization, machine learning, and intelligent building control. Welcome, Kyri, and thank you so much for being here. I'm going to hand the webinar controls over to you now.
Okay, thank you, Amanda. And thank you, everybody, for joining me today in this virtual webinar. So I'll be talking at a high level about how COVID is affecting the electric power grid, and then I'll go a bit more into detail for those of you who are interested. So before I get into the details, broadly speaking, the way that COVID has impacted the electricity grid overall is lowered electrical demand. So the grid is experiencing much lower demand levels than normal operation. People are starting to say that weekdays now look like weekends because people are staying at home and using more electricity in the residential side versus the commercial side. And this has resulted in a wide variety of effects on the grid, such as decreased electricity prices. Now we have less expensive power plants coming online to supply electricity. A subsequent decrease in emissions. This is also partially due to the transportation sector decrease in emissions. Generally a higher use of renewable energy, although I'll get into that a little bit more. And thankfully, no major problems have been observed in the grid so far. So we've seen a really reliable and a resilient operation of the grid throughout the pandemic. In the next half hour, I'll talk about a couple aspects of this. I'll do some background on how people normally consume electricity. And then I'll talk about how this is changing under COVID, the impacts on renewable energy integration, and all of the economic impacts that this lowered demand and changing demand patterns have had. Okay, so how do people normally consume electricity? I saw a survey once where they asked people on the street what they thought the main electricity consumer in their house was, and most people said the refrigerator. This is actually not correct. If we look at residential buildings, which is about 37% of the use, the overall use of electricity in the US grid, we see that a lot of the electricity consumption within residential is due to HVAC, water heating, appliances, electronics. Lighting is getting, so this plot is from 2013, the lighting sliver is getting smaller because of LED lighting and efficient lighting. Within the commercial sector, which is about equivalent to the amount of electricity consumed by residential in the US, we also have a large portion to HVAC and lighting and other appliances, computers. And then industrial sector, so factories, manufacturing in the US consumes the majority of the rest of the electricity generated. You can see that transportation, which is a small sliver here, is increasing with the electrification of the transportation sector, but is still currently a very small sliver of where the electrons flow. So just to be clear, what I mean by residential is probably where most of us are right now: homes, apartments, multifamily housing. Commercial, you can think of as office buildings, restaurants, stuff like that. And then industrial is separate from these two: factories, construction, agriculture, manufacturing. So about half and half of the electricity is split between commercial and residential. And as we know, there's been a large shift because of stay-at-home orders from people going from working in commercial buildings to working from residential buildings. And this has dramatically changed some aspects of the grid. So let's take a look at New York City, for example. And this data, all the data I'm showing here, I pulled from publicly available websites. You can do so as well if you're interested in looking at some data yourself. In New York City, from April 1st to 3rd in 2019, so last year, we had 3 days of a demand pattern that has this general shape. And this shape is observed in most areas of the US. And the shape is comprised of this peak when people wake up. In New York City, it's less dramatic, but you can see it in California a little bit more. New York City doesn't really sleep. It's continuously consuming power for more times than most other areas. In the middle of the day, there's sort of a dip and a flattening when people move from residential buildings into commercial buildings. So the commercial buildings have generally more efficient HVAC, more efficient appliances than in homes. And then there's this small dip and flattening in the middle when people go to work. And then there's a second peak when people come home, they start cooking, they turn on electric stoves, they turn on the TV, turn on the lights. And this curve is generally the general trend of electricity consumption we can see in most cities in the US. Okay, so this is pre-COVID, pre-stay-at-home orders. Now let's take a look at those same 3 days in 2020. So you can see that the overall demand shape is relatively consistent. It's a little bit flatter, kind of hard to see here, but overall we get a large reduction. And so how large is this reduction? It's about 20% reduction, or 1,000 megawatts. And just to give you an idea of how much 1,000 megawatts is, 1,000 megawatts is roughly all of the solar power installed in Colorado. So there has been a big decrease from commercial buildings consuming less electricity, a lot of businesses shutting down, to people moving at home and consuming more electricity during the day. Now, this is New York City. It's one of the more extreme cases. You won't see this dramatic of a drop in everywhere in the US, but it is a very interesting shift in electricity consumption that's resulted in less power plants turning on and less power plants supplying electricity. Okay, the only data that I could get on a granular scale for residential was my own home, and this was taken with my Copper Labs sensor, which is a company in Boulder, Colorado that makes this wireless monitor that you can monitor your electricity consumption. I picked 2 weekdays to compare for my own home. I picked Thursday, February 13th, and then after stay-at-home orders, Monday, April 13th. And I picked these 2 days because they're weekdays where I'm normally at work, and they're also similar temperatures, so I should have roughly similar consumption patterns. And so if we look at the power consumption, so this is over a single day, pre-COVID, I have very low consumption in the middle of the night. My furnace is gas, so it's not going to show up on these plots here. Get up, turn on the computer, turn on the microwave to heat up breakfast. I'm at work, meaning I leave my house, I go to CU, and then there's really low electricity consumption in the middle of the day when I'm at CU. And then you can see when I come home after 6 and there's this spike because I'm cooking dinner. And then right before I go to sleep, there's another huge spike because I like turning on my electric heater in the bedroom before I go to sleep. Electric heaters are notoriously not very efficient, and that's why it's such a huge spike. The one I have is essentially a giant resistor, and you're pumping current through it to get it to heat up and then blowing air across it to get it to blow that hot air into the space. So after COVID, you can see that there's a lot more demand during the day. Me and my wife are home on our computers working remotely. There's a lot more lights that are turned on. There's a lot more use of like the stove and the microwave and the toaster oven in the middle of the day. And then we get the same 2 peaks in the evening when we're cooking dinner and then going to sleep. And so I just drew this line at 2 kilowatts here so you can compare just an arbitrary line. You can compare how the peaks have changed pre and post COVID. This would be a lot different, and the electricity consumption would be even more increased if I had an electric furnace instead of a gas furnace. But it's increased from 12 kilowatt hours to 16 kilowatt hours, which is pretty significant. That's a 30% increase in electricity use. So at the residential scale, increasing, commercial scale, decreasing. I'm not going into work. Okay, so we looked at New York. We looked at a case of a residential building in Boulder. Now let's take a look at Texas, specifically the ERCOT region, the Electric Reliability Council of Texas. It covers this dark blue region in the plot on the left. And ERCOT is mostly a self-contained grid. It does have connections to other grids, but it's sort of its own grid system operator that's operating and maintaining power generation within that region. So looking at 3 days, and I chose these 3 days because they're all weekdays. So March 25th through 27th, I believe, was a Wednesday through Friday, and March 25th through 27th, 2019 was a Monday through Wednesday. And you can see that 2020 versus 2019, pre-COVID stay-at-home orders, there's a large increase in 2020. And we'll get into why that is in a second. And this is much larger, just to give you an idea, than the New York City case, because now we're looking at the majority of Texas. This is about 10,000 megawatts, which is huge. So after the stay-at-home order in April, we now see not only a flattening of the demand curve in 2020, but also a reduction. And so there's a lot of things going on here. What I want you to get out of this talk is not that COVID is purely the reason, stay-at-home orders are purely the reason that electricity consumption patterns are changing. There's also multiple other factors. So why is 2020 demand in March so much higher than 2019 demand, 10,000 megawatts? This is because if we look at temperature, which is a huge driving factor of electricity consumption within buildings, the temperature in 2020 was just much higher during these days than the temperature in 2019. So for example, on the 26th in 2020, we had a high of 90 degrees. In 2019, we had a high of 81. Same with the 27th, the high of 89 versus 79. So it's not that overall COVID has, resulted in a huge impact. It's also factors from temperature and other factors, which I'll get into in a second. So it's, as I said, it's not as simple as stay-at-home reductions. So you might think that the decrease here is purely due to stay-at-home orders. But if I look at April versus March in Texas, so this is San Antonio, I just picked somewhere that's roughly in the center. Thank you to everyone that helped me with Texas geography when I was doing research for this presentation. So we can see that in 2019, the temperatures were just much higher, so the cooling load in buildings is going to be higher. So this decrease isn't just due to more people staying at home and businesses not consuming as much electricity, but it's also due to cooler temperatures. So there's a lot of dynamics that are interacting and interplaying here. Now, not everywhere is experiencing the same effects. So what we looked at just now was mostly due to people in residential buildings consuming more and consuming less in commercial, but let's take a look at the industrial sector as well, and the power consumed by the industrial sector. So here's a map of the blue dots represent the active oil drills, and this is concentrated a lot in West Texas. This area has very little residential load. Not many people live right next to these. In this region right here, in Houston, the Houston metro area, there's a lot more residential consumers, so we're going to see that general shift from COVID. So let's first take a look at the West Texas, where the oil drilling is happening. So compared to 2019, which is the orange line, the power during COVID times, post stay-at-home order, is actually still increased in this area. And this is due to an increase in oil drilling from 2019 to 2020. Not a lot of residences, not a lot of people live and sleep and work in these areas other than in the oil industry. So we don't see this dip that's resulting from stay-at-home orders. This is in contrast to in the Houston area, where we see that in 2020, we do have a decrease in power consumption because it's a more residential area. So if you look back in 2018, in the electricity consumption in the West, it's even decreased further oil drilling has increased over the years in the west region of Texas. Now, this isn't to say that COVID hasn't had any impact on oil drilling. There's been a lot of different effects that are into play here. So many of you are probably aware that there was this huge dip in oil prices. So you can see from this wonderful website called oilprice.com that you can see the price of oil, dollars per barrel of crude oil, and how it has dipped dramatically in recent months in April and May. And so the demand due to this dip in oil prices has changed because there's been some shutdowns and reduction in oil drilling due to the drop in oil prices. So if we look at past, not looking at the potential impacts of the stay-at-home order, but looking at the impacts of the oil prices, we can see that there has been a decrease when the prices of oil dipped so low versus when the price of oil was slightly higher. Okay, so lots of factors, temperature, economics, not just people staying at home that's impacting the grid. So the takeaways here, there has been a decrease in commercial load and an increase in residential, but because we have this, residential consumes slightly more electricity than commercial, we have an overall decrease in electricity consumption, in some cases like New York City by 20% or by a very large amount, and a change in usage patterns. We now have this more consumption locally during the day and less consumption in businesses and office buildings during the day. Okay, so what does this mean for renewable energy? A lot of the questions I got in the RSVP form, I'd say about 75% are about renewable energy. So hopefully I can answer some of those questions now. And then the renewable energy impacts actually play a lot into the economic impacts. So we'll talk about that briefly as well. So for those of you who aren't familiar with the problem with solar energy, I will teach you this now. It's one of my favorite things to talk about. My students always make fun of me because apparently I talk about the duck curve in every presentation I give. But here's the demand in California under the region that's governed by the California Independent System Operator. And you can see that this has a more dramatic shape than what I was talking about before in New York City, where people get up and there's a spike, there's a dip in the middle of the day when people go to work, and then there's another spike when people come home. This is over a 24-hour period. This is just the electrical demand in the CAISO region. If we subtract the renewable generation, so in this case just solar and wind, we get what's called the net demand. So the net demand, or this purple curve, is what the other power plants have to supply to people consuming electricity. So you can see that there's, in this particular day I'm looking at in February, there wasn't much wind during the morning. There wasn't solar generation because the sun hasn't risen yet. So the net demand roughly matches the overall electricity consumption from buildings. We get this dip in the middle of the day when solar is generated. And so now the amount of electricity that has to be provided by conventional power plants is much lower because we're taking a lot of that from solar power. And then as the sun sets, we get more electricity that's required to be produced by conventional power plants. There's a little gap here that's probably due to wind generation in the evening. So this net demand curve, which is especially pronounced in areas like California and Hawaii, where there's a lot of solar, is what we call the duck curve. And some people call the duck curve solar energy's greatest challenge. And the reason the duck curve is bad is not because we don't like ducks, but it's because we have these sharp ramps when the sun rises and sharp ramps when the sun sets. And the problem with this is a lot of conventional power plants like coal, gas, nuclear might have to reduce their production extremely quickly to keep up with the sun rising, and then increase their production extremely fast when the sun sets. And for slower power plants, this is challenging to do, and also not economical for them to shut down for a few hours in the middle of the day and then start up again. Shutting down and starting up can be very expensive, and in some cases technically not possible for some of these conventional power plants. In the middle here, we get this dip, that's the duck belly from the solar, and the dip is continuing to get deeper and deeper. The duck is, gaining weight as time goes on because more solar is being installed in the grid. So this problem is generally getting worse in many areas, the duck curve problem. Okay, how does the duck curve change under COVID? So let's take a look at, that was February, let's take a look at April. You can generally see that it looks like this demand curve is much flatter, and that's because people are filling in the belly of the duck by working from home and using more electricity in the middle of the day. If we subtract the solar generation, we can see that again, the duck belly is less saggy, it's flatter, so we're getting more electricity consumed in the middle of the day, and the ramp severity has decreased. So previously, in the day that we looked at before, it was 13,000 megawatts. Now it's 12,000 megawatts, the amount of power ramp that we see when the sun sets. Looking at these side by side, it's actually not that dramatic. So the ramp is still pretty bad in the post-COVID case. And the reason is that even though people are consuming more in the middle of the day and flattening the curve, not to use COVID terminology, but people in electricity were using flattening the curve before this happened. If we're flattening this demand curve, then we're getting a slower ramp, but the demand overall is much lower. So it's not as much electricity is consumed in the middle of the day overall, even though it's flattened. So you can see this in the left-hand side, pre-stay at home. We have roughly a 25,000 megawatt peak in this area of California. And then after COVID, we have roughly a 20,000 megawatt peak. So we are flattening, but we're not consuming enough electricity to completely fill out the belly of the duck. So using more renewable generation is good. So overall, this is making it easier to mitigate those ramping problems that conventional power plants can't always keep up with. So overall, good. So what is this doing to electricity markets? So typically, in many cases, like rare events such as natural disasters, heat waves, blackouts, windstorms, have an overall negative impact on prices. We've seen price spikes in many areas due to storms because it gets more expensive to deliver electricity to consumers. Heat waves, people are consuming a lot of power. We might have to turn on an emergency backup power source, which is expensive. And so generally there's a negative impact on prices. Under COVID, it's very interesting because prices are actually decreasing. So decreased demand means we have to turn on less power plants, there's less losses in the system, and overall the electricity prices are lower. This was resulting in market participants, so people participating in electricity markets, meaning in areas with markets, is shown in this plot over here. These participants are making overall less money. So not just for those of you who aren't as familiar with electricity markets, not everywhere in the US has a competitive market. Some areas are still vertically integrated, meaning that there's one company that owns the generators, that owns the lines, that operates parts of the system. And in some areas it's competitive, like in ERCOT, New York ISO. And in these markets, the generating companies and market participants actually submit bids to the market with the amount of electricity that they can supply at a particular price. So these market participants are resulting in less revenue for these generators. Taking a look at New York City again. So here I have the blue ones as April of 2019, pre-stay at home. And these teal ones, sorry if you're colorblind, I didn't think about that until just now. These teal ones are the days after stay-at-home orders in New York City. On this axis right here, it's 5-minute increments throughout a 24-hour period. And on the z-axis here, the vertical axis, it's the cost to deliver electricity to New York City. You can see that during normal times, 2019, we have relatively high prices with price spikes when it gets expensive. There's a lot of people consuming electricity during that time, and it's hard and expensive to get more generation to New York City. Post stay-at-home orders, we have much lower demand. We have still have price spikes, and this is due to a plethora of reasons, which I won't get into too much in this talk, but generally you can think of these prices as the cost to deliver electricity to New York City. We have some price spikes still, but overall you can see that these curves are much, much lower, meaning that the cost to deliver electricity to consumers is much lower. In many areas, electricity prices are actually going negative. So people were aghast when oil prices dropped so low, but in electricity, it actually happens all the time that electricity prices drop negative. And this is happening more frequently under stay-at-home orders because the demand is so low. So here's a plot of the California Independent System Operator, ISO, and you can see that in some areas, the cost to deliver electricity to that area is actually negative, meaning that you could get paid to consume electricity. Now, this doesn't currently impact residential consumers who are sort of locked into a rate in most areas. It would impact bigger consumers who are buying and selling and playing within the market. And this happens, electricity prices go negative because in many cases, supply is exceeding demand. There might be some situations where there's a lot of wind at night. Instead of curtailing the wind or disconnecting the wind from the grid, they'll actually pay people to consume that wind so they don't have to disconnect the wind. With the duck curve, this happens because instead of curtailing the solar or disconnecting the solar from the grid, or instead of turning off power plants in the middle of the day, we just pay people to consume a little bit more to fill in the belly of the duck so we don't have to turn off a coal plant, for example. And because turning off that plant, again, is expensive, and then turning it back on in the evening is expensive. So it's actually cheaper to pay people to consume a little bit more to avoid turning on and off the plant or to avoid curtailing renewables. So this is a very interesting phenomenon that's increasing negative electricity prices. The prices you can think of as a proxy for how efficient the grid is delivering electricity to consumers. So this is the same plot as before, except now instead of looking at price to deliver electricity, I'm looking at the cost of losses. So if I have a really expensive power plant that needs to deliver power to New York City, that power has to travel a very long way. So there's going to be losses due to heat in the power lines as the power is traveling through the line. And it's also going to be potentially from an expensive source rather than from a cheap local source, for example. So piping in power from expensive generators and also from far away results in an increase in line losses. And the increase in line losses, you can see the line losses overall decrease under COVID because we have less congestion in the system. There's less people taking up all of the usable infrastructure to supply power to New York City versus in pre-COVID times when there's a lot of losses and a lot of congestion. Again, this is a very high level view. There's a lot of nuances that go on in power grids. It's very unlike any other market because we can't always control where the electrons flow. There's a lot of economic restrictions that have to be tied to physical restrictions, making electricity markets very, very interesting and very different than, say, a barrel of oil, which is the common comparison that's made. Okay, can we do anything? Can an individual building owner do anything to help renewable integration? So I just wanted to make a quick plug for my lab at CU Boulder. We call ourselves the Griffin Lab, and this stands for Grid Interactive Frameworks for Intelligent Infrastructure. And we look at problems that span both residential and commercial buildings, as well as industrial buildings, to large-scale renewable energy integration and large-scale ways of operating the grid more efficiently. So some of the questions that are interesting to answer, not just in COVID times, but pre and post-COVID, how can the grid operate more optimally? How can we reduce these losses? How can we improve the use of renewable energy? How can buildings play a part to help the grid? So traditionally, it was mostly the supply side that did a lot of the work in the grid. Balancing supply and demand was done a lot by the supply side. But now that we have a lot more connectivity with our appliances at home, we have smarter devices that are able to respond to signals from the grid. Can we use these smart buildings to help shift when we use renewable energy? So you might be familiar, you might have gotten, for those of you in Colorado or in a region that has time of use pricing, you might be familiar with Excel trying to get you to enroll in their time of use pricing or TOU program. And this is a form of what's called demand response, which is the demand side responding to a signal from the grid. or in general, the demand side changing the way that they use electricity to help the grid. And the time of use pricing versus normal electricity pricing charges you a different price of electricity depending on what hour it is. And this is to incentivize people to use electricity during times when it's cheaper and during times when the grid can operate more efficiently. So in Colorado, in Boulder, where I live, this is the time of use pricing rate, which I'm currently under. Between 2 to 6 p.m., it's getting really, really expensive, meaning Xcel's trying to decentivize me from using electricity from 2 to 6 p.m. And from 9 p.m. to 9 a.m., it's really cheap. They want me to use more electricity during those times because the grid is less heavily loaded. Now, how has this changed under COVID? So this was the TOU pricing before COVID. We got this email that allowed us to opt out of the time of use pricing because Xcel realized that people's demand patterns are going to change dramatically. It might be hard for us not to use as much electricity during 2 to 6 p.m. And so they offered us this opportunity to opt out of TOU pricing. So choosing when you run major appliances can help the grid. And again, this structure is going to look totally different if we're in, let's say, California. It might not be as expensive to use electricity at 2 p.m. because there's a lot of solar generation during that time. Another area of research is not just looking at how an individual building can interact with the grid, but looking at aggregations of buildings. So here we have on the left-hand side, just some of our current research is something that allows a building to interact with the grid in a seamless way. So asking people to change when they do the laundry, to change when they take a shower, when they turn on lights, when they turn on TV is really, really challenging. We have those ingrained behaviors. We're used to consuming electricity when we want to. We're used to flipping on a light switch and just not thinking about where those electrons come from. So really these systems that interact to these prices and interact to the signals from the grid have to be seamless. They have to be low impact on our lifestyle and on the way that we currently live. So you might not know when your air conditioner is on, but as long as it's cool enough for you in the house, you don't really care. So we can do things like pre-cool the house during times when there's a lot of solar, and then by the time you get home or in the evening, that your house stays cool. It has that thermal mass that maintains that temperature. It doesn't instantly get hot. So we've shifted when we use the air conditioning to a time that overlaps with more renewable generation. So our research right now is just looking at how we can coordinate a large amount of buildings in a seamless way to achieve grid objectives like integrating renewable energy. And this would involve having residential buildings communicate with commercial buildings. We propose sort of a market framework for this to happen, where the building will automatically determine how much flexibility the owner has to give just based on what it has learned over time about what you like and what you don't like. And it communicates that to the grid, and the grid decides sort of what signal to send back to change how you use electricity automatically. There's a lot of other problems with these time of use prices. So this is a one-way signal in Xcel's case. They're setting these prices and just hoping that people respond. There's no guarantee that everyone is going to stop using electricity during this time. So these traditional demand response programs offer no guarantee, or I shouldn't say traditional because the very old demand response programs do offer a guarantee, but the time of use pricing at the residential level doesn't offer a guarantee because there's no predicting how many people are going to respond. And it's very challenging, especially during COVID times when our patterns have completely changed and the grid forecasting models are thrown off by all these new demand patterns. So with this two-way framework where the home communicates back to the grid with their flexibility, we can avoid some of those problems and know who's going to respond and roughly what the demand reduction will be. Okay, so to dive a little bit into the weeds, this is some work done with my PhD student, Caitlin Griffin. We're looking at not only can homes respond in an intelligent way to grid signals, but also how do they do so under uncertainty. So there's a lot of uncertainty in buildings, especially residential buildings. There's uncertainty with occupancy, there's uncertainty with outdoor temperature, there's uncertainty with what the actual models of the appliances are in the building. And so we're implementing something that's called chance constraint programming, which is we have the indoor temperature, it has to stay below whatever the maximum temperature the user set is, and it has to stay above whatever the minimum temperature the user set is with a high probability. So that's the PR. And so because outdoor temperature and all these other factors are uncertain, they're random variables, they're stochastic, this constraint is going to be uncertain. How do we know if we turn on the AC now instead of an hour later that we're going to be able to satisfy the temperature bounds that the user set? And we don't know. So we're trying to satisfy this with a high probability. So that's what these constraints aim to achieve, is that the indoor temperature and other constraints that the homeowner sets are satisfied with a 95% probability. So if we can save you $2 by making you slightly uncomfortable with a 5% probability, that's worth it to most people, rather than ensuring that your home is always 100% of the time within bounds, but then not having any monetary savings. So as we see here in this plot at the bottom, this dashed red line is the outdoor temperature over a 24-hour period. The homeowner receives a notice from the grid operator saying, whoa, it looks like it's going to be really hot. The grid's going to be overloaded. I'm sending a request. I'll give somebody some money to reduce their electricity consumption during 4 to 6 p.m. So the home receives this signal, and then what it does is it starts cooling. It starts pre-cooling the house so that during the high cost period where the homeowner can save money, it doesn't have to turn on the air conditioner. The house just naturally stays warmer. And the amount it decides to pre-cool is based on what it forecasts the outdoor temperature will be and how we can satisfy this constraint with 95% probability. So that's just a brief part of what we're doing in our lab. And to answer some of the questions I got about long-term effects of COVID-19 on the power grid, these are likely mostly temporary benefits. So we shouldn't lose sight of our sustainability goals. Maybe you saw that New York Times article that says, oh, there's 11% or 18% reductions in carbon emissions due to stay at home. This is great. We shouldn't let this distract us from our main goal of integrating renewable energy into the grid, because these aren't going to be long-term permanent changes, likely. Solar panels and wind turbines alone won't solve climate change. So on the demand side, we have to learn how to use electricity in a way that coincides and jives with the way that the grid is operating. Our grid has proven resilient so far through the pandemic. So this is a very good thing. Unlike other large-scale blackouts and storms and hazards, the grid during COVID has been really resilient and really reliable. And I would just like to thank the members of my lab, and also special thank you to those who I consulted with during this presentation, especially about all of the nuances of Texas's electric power grid. And with that, before we go to questions from the audience, I would like to take some of the questions that I saw in the RSVP forums and answer those, because there were some general themes. So there was a lot of questions about general renewable energy integration, but I just wanted to inform you that I'm going to focus on the questions that are COVID impacts on renewable energy integration. So a lot of you asked me, what is the long-term effect on renewable energy integration? Like I said, the short-term effect is that there is more solar being utilized. There's actually in some areas less wind being utilized, because the reduction in demand has resulted in less power from wind being consumed in the mornings and evenings. So that has actually resulted in more wind curtailment in some areas, but overall increased solar usage. Long term, again, as I said, I don't think we should be distracted too much from our goals of carbon reduction and renewable energy integration. How can we apply lessons learned from COVID to increase grid robustness? So this is a really good question. And as I said, thankfully, because this has mostly resulted in demand decreases, there hasn't been a lot of issues with the grid like other hazards. So the lessons that we can take away, I think, are that the grid needs multiple parts to be working in unison in order to be effective. So we can't just continue to rely on, let's say, the supply side large-scale power plants to solve every issue. The demand side is what consumes this electricity that's being generated. So the balance between these two sides, I think, has to increase and be more seamless in order for us to have a continued resilience in the grid. Is increased use causing grid to be more often outside specified voltage limits? Okay, this is a good question. I would have loved to get into this a little bit more. So the increase in electricity use at the demand side has actually impacts on the grid that I didn't talk about here. So when you look at these websites that show you overall demand in New York or overall demand in ERCOT region of Texas, you'll say, oh, this is great, the demand's decreasing, everything's positive. But the increase in demand at the residential level has actually caused some voltage problems because people are consuming more in certain areas of the grid and less in other areas of the grid. So the voltage, I'm trying to explain this in a super non-technical way. There has been fluctuations in voltage due to power being consumed spatially in different locations. This is in contrast to just looking at the aggregate consumption. Will certain services have to increase production for future crises such as COVID-19? How will that look like? Increased production, at least in terms of the grid side, probably not. This does sort of emphasize, you know, people's, before maybe you weren't thinking about your impact on COVID, but now after this presentation, maybe you're starting to think, wow, you know, there's a lot of solar energy that could be used in the morning and the evening. So this might incentivize people more to look at not only energy storage resources, but inherent storage resources such as pre-cooling and preheating buildings. So there could be more of an argument for a lot of these services now that we see an increased benefit with these different situations the grid can be in. What is the impact on coal-based power generation? So this gets into how electricity markets, so if we're just looking at a region that has wholesale electricity markets, the way that those markets are cleared is generally resources bid into the market with the cost that it is for them to produce electricity. So for example, renewables have a very low cost of producing electricity, so they might bid in at close to $0. Coal is relatively expensive, especially with advancements in fracking. Natural gas generation has gotten much cheaper over the past few years. So coal might actually be one of those expensive generators that do not get selected in the market anymore because the demand is lower. So overall, a decrease in coal power generation. And then I wanted to hand it back to Amanda and see if we have any additional questions from the audience.
Great, thank you, Kyri. As a reminder, please feel free to submit your question through the Q&A interface and we will ask Kyri. Let's start with a question from Jeffrey. Can you share more about how you anticipate things returning to normal, or whether you believe there will be permanent changes to when and how people use electricity?
So I can't speak to things returning normal outside of the electrical aspect, but when I say that I think things will be roughly returning to normal, within a lot of these large office buildings, there's not extremely granular control that says, you know, only turn on lights in this region if a person is in this region. The occupancy detection and control is not extremely granular. So what will end up happening is, let's say 80% of people go back to work in a particular office building or commercial sector. A lot of that same electricity consumption that building was consuming before with 100%, it might be very close to what is being consumed with the 80%. So I think things will generally trend as people go back to work and go back, restaurants continue to open, stores continue to open. Even though there might be less people in them, the electricity consumption is going to trend towards what it was before. Maybe not instantly, but I think it will get there.
Okay, great. Thank you. Next, we have a question from Lily. How have COVID-19 related load changes affected utilities' load forecasting algorithms?
That's a great question. So from what I've heard, I haven't spoken to the utilities directly, just people who work with utilities. It has thrown off a lot of these load forecasting algorithms very significantly. So to give some of you some more background, the utilities generally have a prediction method that looks at, you know, the forecast for temperature and whether or not it's a weekday or a weekend and other factors to determine how much power people are going to consume in subsequent days. And that gives them an idea of what power plants are going to be selected to be turned on. And so a lot of these forecasting algorithms are completely thrown off because we don't have historical data that represents COVID situations. So it's confusing a lot of the utilities.
Okay, thank you. Next, this question comes from Anonymous. How are areas or energy communities which are autonomous in energy production or include delocalized energy storage capacity affected by increased residential consumption?
That's an excellent question as well. So I think what Anonymous is getting at is that, so there's some areas that, for example, part of CU's campus who have localized generation, in some cases storage. You can think of these as microgrids in some cases where some of them are able to disconnect from the main transmission grid and be offline or isolated for multiple days or even longer. And in these cases, the increased consumption from residential could be really, really dramatic because we're not used, again, these resources that are supposed to supply power to a small constrained area aren't used to these new load patterns or having to supply electricity for that long. That said, a lot of microgrids right now aren't mainly residential. So the decrease in demand, for example, at CU or in other areas with microgrids, downtown districts, other college campuses, they won't be struggling as much because the decrease in demand is a lot easier to deal with than an increase in demand.
Okay, thank you. This next question is from John. Coal and other traditional units also have operational restrictions for starting and shutting down the coal and nuclear besides the cost of shutting down the generation. What are your inputs on impact/motivation on battery technologies with renewables to avoid the change in load patterns due to external impacts like COVID-19?
Yeah, that's a good emphasis. I think I only mentioned it briefly, but John is right. When you start and stop coal plants, it's not just economic considerations, it's also technical considerations. For example, in the US, a lot of the nuclear plants are close to producing at their maximum capacity. They're what's called baseload plants. So they're not ramping up and down or changing their output as much as in other areas, like in France, where these nuclear plants ramp up and down all the time to balance fluctuations. So there's a lot of other considerations. The aspect of storage, so storage is a tricky example because right now at an extremely large scale, as you saw with CAISO, in order to integrate, let's say if we wanted to store that entire duck's belly into a battery, that the capital cost of that battery would be really high. And then depending on the way we use the battery, it could degrade the lifespan of the battery rapidly. Another aspect which is not always considered is the environmental impact of creating and producing these batteries. Mining for lithium, disposing of the batteries properly. And there's an environmental impact that comes with energy storage that doesn't make it the perfect solution for renewable integration, unfortunately.
Okay, thank you. Next, we have a question from Joseph. Do you have any idea about how changes in the water sector could affect the electricity grid? For example, water treatment and pumping.
Okay, so before I get to the water treatment and pumping, there are a lot of interactions between water and energy that are directly applicable to generation, for example, in hydropower. So with increased droughts and decreased water supplies, it's going to get increasingly difficult to rely on hydropower. This is seen in, for example, Venezuela. I think in 2016, there was a big drought and the Guri Dam, which supplied electricity to a large portion of Venezuela, did not have enough water capacity to supply electricity. So what happened was they had these rolling power outages for citizens where they'd have multiple blocks of hours at a time where people didn't have electricity. And this is done in a lot of countries. So as this interplay increases and electricity from hydro is potentially threatened, we're going to see an increase in price and increase in need for generation from other areas. So in the Pacific Northwest, where we have a lot of hydropower generation, we're going to have to get potentially more electricity from other areas. In terms of water pumping and use of electricity at water treatment facilities, these facilities do consume a significant amount of electricity. I forget the actual number. I want to say it's like 7% or somewhere around there of electricity consumption in the US. I don't think these will be extremely heavily impacted. There's a lot of other loads that will be shed before the electricity used for water distribution is canceled.
Okay, thank you. We'll take two more questions. The second to last question here is from John. What is the potential of energy efficiency in building codes, short and long term, in making renewable integration more successful?
So I think energy efficiency is a really big part. The only thing with energy efficiency is that in general, consuming electricity is good, but we also need to change when we consume that electricity. So it's not just about the metrics and, for example, new building materials, more energy efficient devices, appliances, stuff like that, but also the use and intelligent control of those devices. So if we have residential buildings now having variable frequency drives, that could be used for providing grid services like, you know, balancing fluctuations from your rooftop solar unit or providing some kind of regulation services for the grid. And so I think all of these pieces have to come together in order for us to achieve a cleaner electric grid.
Okay, thank you for that. And our final question here comes from Chris. What has COVID-19 taught us about the ways that states and grids can get to zero carbon with the highest quality of life?
Highest quality of life. So in my opinion, highest quality of life is zero or close to zero carbon emissions, reliable power in terms of the grid, reliable power delivery, economic justice in terms of electricity pricing and emissions and availability. COVID has taught us, first of all, that the grid is resilient. We have built the grid with a lot of redundancy, even though many components of the grid are aging. Something like 70% of transformers are over 30 years old. The grid is aging, the infrastructure is lacking in a lot of areas, but it has taught us that the grid is resilient. And I think it has also brought to many people's attention how sort of the grid operates, because a lot of us don't think about it, as I was saying before. So the renewable integration lessons learned from COVID are that it's not just energy demand decreases that need to happen, but also, like I said before, a change in how we use electricity, because as I was saying, there's wind generation that's being curtailed in the evening because people aren't using as much electricity. So it's not always about purely demand reductions.
Great. Well, thank you so much to everyone for joining us for today's presentation, and a special thank you again to Kyri for this great information. As a reminder, all webinar attendees will receive an email tomorrow with a link to the recording of this presentation. To view upcoming webinars as well as previous recordings, please visit our website at colorado.edu/business/alumni. We hope that you will join us for our next webinar, which is tomorrow, as Professor in the Department of History, Dr. Susan Kent, addresses COVID-19 lessons learned from the 1918-1919 influenza pandemic. In the meantime, have a great rest of your day and go Buffs!